Last class, what you have seen? Can anybody remember what you have seen last class? Last lecture we have seen the gravimetric analysis. And can anybody chip in or try to help me out? What is the gravimetric analysis? What does it mean, gravimetric analysis? Gravimetric analysis is, I hope, or I sincerely wish that you go and, you have studied, but gravimetric analysis is, we precipitate, we need to form a precipitation when there are two reactions occurring. There is a reaction occurring between two species, like reactant A and reactant B. They are reacting together and the precipitation is forming. That precipitation means a solid forming out of some liquid medium, like reactant A, reactant B, both we are mixing liquid, and then our subject of our interest, what we want to know or want to analyze, is forming a precipitate. That means is forming a solid. We are taking that solid, we are filtering it out, removing excess of water, right? And then to remove further moisture, we are drying it. And then after the dried, no moisture content, no water inside that solid, we are weighing it and finding out the mass. So that is called the gravimetric analysis. Now, volumetric analysis. What if we cannot form a solid out of mixing two liquids? So to be more precise, to be more clear, that it is not, gravimetry is not always two liquid and forming a solid. It can be one solid, one liquid, and forming another solid. That is also can go. Okay, so volumetric analysis now is that we are, so what happens if we cannot form a solid out of those liquid, reactant A, reactant B, and product C is forming, right? But the product C, we cannot produce any solid. So what? We cannot analyze it? We can, because the scientist has come out with a very genius technique that even it does not form any solid by knowing the concentration of that two things that we are mixing and the reaction, how the reaction is going on between them, we can find out the other reactant that is in the solution that we are adding. So now you are, I hope that you already understand that volumetric analysis is analyzing by based on its volume, and of course with the concentration. But what we can see, concentration we cannot see, right? Concentration you cannot see. You know the concentration, you can calculate the concentration, but you cannot see. But the volume we can see is 50 milliliter, 100 milliliter, 1 liter, 5 liters. So we understand where we can see the volume. That is why the name came from the volumetric. All right. So for us today, the objective of, that we want to learn is standard solution. How do you prepare the standard solution? All right. We want to prepare the standard solution. What does a standard solution mean? Standard solution, I think it will come later on, but standard solution is that we know that this is this concentration. All right, this is this concentration, or we know the strength of the solution. We are very confident. We have prepared ourselves. We know the exact calculation, and we can use it for any other chemical analysis with certainty, or with very much, or with very much assurance that, okay, we are very confident, this is the solution. This is the strength of the solution. So that is the standard solution. And to know to prepare the standard solution, we, as I said, that we should be able to know the concentration of the solution, right? We should be able to measure the concentration or calculate the concentration. So how do we calculate the concentration? We have to also understand how to calculate the concentration of a solution. And that can be mole per liter, what is we call molar or molarity, or gram per liter as well. And what can be, weight by volume percentage. We are coming later on. What are those means? So, and later on, afterwards, when we are preparing the standard solution and the concentration of the solution of the different solution, we can find out the acid-base reactions. And that is our target, because when we mix together, there must be some reaction going on inside, and there should be an outcome. If even though it does not produce any solid or precipitation, it must do some reaction. Based on that reaction, we will be able to find out the known concentration of the other or known amount of the other reactant that we used, and it will be based on the stoichiometric ratio. At this point, can anybody tell me what is stoichiometric ratio? Or what is stoichiometry? Can anybody tell me? My camera is on. Just let me know. Is the broadcasting okay? Is it lagging? Should I turn off the camera?
Not right.
So I keep the camera or I turn off the camera? I am worried that maybe it is taking the bandwidth, so maybe the video will be lagging for you. Okay, I'm counting to 3. Please tell me if I should turn off the camera. Counting 1, twice. Okay, so no. All right, so I'm keeping the camera on. Now, oh, my question was, what is stoichiometry? Thank you. Shamad, Bilal, Vanessa, thank you. What is stoichiometry? Can anybody tell me what is stoichiometry? And I mean, it does not have the exact definition. Just what is the idea? I mean, what do you understand about it? Just tell me. It doesn't have to be the correct, very book definition from the book. No. Yes, Danesh.
So I'm not sure. So I'm just telling what comes in my mind. Is it okay?
Yeah. That's what I'm asking.
Like quantity. I mean, like a specific quantity of substance participating in a reaction. Like if let's say it's a compound and a compound they react, something like that, right, sir?
Mm-hmm.
I don't know how my accuracy is, but that's my answer, sir.
Exactly. I mean, thank you very much. The answer is accepted. Bilal, I saw that you're typing something. So if it is problematic for you to type, so just unmute and talk. All right. It's an interactive class. There is no marks on it. All right. There will be no marks. So Danesh, yeah, your answer is accepted for this. I saw it. You were typing. Okay. So your answer is accepted for this discussion for the discussion purpose. Okay, sorry, for the discussion purpose, it is accepted. But if it is in the exam, it will not be accepted. Yeah, because you have to write it down, and that is the documented. So I understand what you mean. The ratio, right? The reactant ratio. Yes, exactly. Yeah. The ratio, the reactant are reacting to one another to form a product is the stoichiometric ratio. Remember the number of moles that I always talk and I always stress on it. I told you that I will stress on it till the last of the semester. Moles, This is not a number of kilogram or number of tons or number of liters of the product things that are reacting. It is the number of moles they are reacting. And when we will know that what number of mole is reacting to what number of mole to form a product, that is the stoichiometry. All right. So another way you can say that stoichiometry is the balancing out the reaction, chemical reaction, of course. There are many types of reaction, right? Emotional reaction, physical reaction, but we are not talking about those things. We are talking about the chemical reaction. Of course, the emotional or physical reaction that also has a relation to the chemical reaction that is occurring in our body, in our brain, but that is too far-fetched thing. We are not discussing. Probably when you go to the higher class, you can think about it. Okay, so yeah, I was talking about this stoichiometry. So when we already understand that how these things are occurring, how this reaction is occurring between one species to another species, then only we will be able to find out the concentration of others. So if you even know how to produce the standard solution, if you also know how to calculate the number of moles or molarity, mole per liter, you cannot find out, you are still not there until you know the stoichiometric ratio. That means what number of moles react to what number of moles of A and B, the different reactant to produce a product. Unless or until we know that one, we will not be able to do the analysis, find out the number of moles or things. Yeah. All right, so we are in analytical chemistry now. We are studying the analytical chemistry. Analytical chemistry means we are looking for something by analyzing the evidences or the clues that we have. What are the clues do we have? So far, we have seen the gravimetric analysis that I already said that it will be due to the precipitation, and then we dry and then we filter it, then dry and then weigh it, gravimetric. So then weight volumetric is the acid-base reaction. And when it is acid-base reaction, it will occur in a solution, right? It will be occurring in a solution, SOLN, in a short form, we write it in solution. So acid and base, they are happening in solution. All right, in solution form, it is occurring. And then, what is that? Okay, and since it is in solution, the volume is important for it. The volume is important for acid and base, both we are adding together to find out the product. I cannot see the chat box, but can anybody tell me, when we add acid and base, what is the product form? The common product. What is the common product that is formed?
Hydrogen, water.
Sorry, what? Munib, yeah?
Hydrogen or water.
Okay. Anyone else want to chip in?
Salt and water.
Yeah, not hydrogen and water. Munib, you are half correct, so you got 50% only. And who replied it here? Chelsea, I think, or Vanessa. So yeah, you got the full point, because it is not hydrogen and water, it is salt and water. So this is like, how do I say, this is a universal truth, okay? When you add an acid and a base, there will always be a salt and a water. Depends on what type of salt. Water is water, right? Water is always the same water, but the salt can be varied, depends on what type of acid and base you are adding. All right. So this is a universal truth. You just remember it all the time, that if you add salt and water, acid and base, salt and water is going to form. So volumetric analysis that I was always taking, that chemical reactions occurring between two substances and in aqueous solution. In aqueous solution, aqueous solution means there is the solution is made with water. So there is in water, those substances are inside the water. We put it inside the water, so that is the aqueous solution. And yeah, please.
So basically, the meaning of aqueous means it has a H2O, right?
Exactly.
Can
Yes.
that way?
H2 is water, right?
Yes.
Yeah.
Just
Yeah.
the compound, the hydrogen.
Yeah. It's more precise way to tell it that way. Yeah. Thank you. So it has water or H2O in it. And so by measuring the volume that require of one solution to neutralize another one, when I'm saying the neutralize, to fully react with another one, we know the known concentration of the other solution. So by having the reaction between them and by bringing the other one, let's say that we want to know the concentration of this solution. There is solution A or reactant A, and this is reactant B. All right. So we want to know the reactant B concentration or reactant B's strength. So what we will do is we know A, this is known to us. We will add this A to B until to the extent where it is not B anymore. It has converted from B to something, to a product that is C. So A plus B will have a product that is C, all right? So it has converted to C until, if it is not converted to C, then we cannot, it is not an analysis. We cannot find out the identity or strength unless all of it goes to C. Okay, so that's why I'm saying that we will be adding A to B to the extent that there is no B anymore in the solution. All of it has been converted or changed to another species. That is, for the sake of our simplicity, we are calling it, let's say it's called C. So it becomes C. So what can be the C? It can be anything. It can be any salt. Depends on what type of acid and base we are adding. All right. What type of acid and base we are adding is primarily for acid and base, but it can be done for other thing as well. But for our foundation chemistry, we will only confine ourselves to acid and base reaction. We will not go beyond that. Okay, so yeah, so A and B producing C. So if there is a trace amount of B left in the solution, it is not done yet, and we cannot find it, or we cannot say for certainty that we have found the strength of the solution if there is a trace amount of B. There is another thing, that if we add too much of A, what if we add too much of A? What will happen? Will it be C as well? Can we take that the value to calculate or do the analysis? Can we? There is another problem. Depends on what type of C is forming here, or what type of compound is forming here, product is forming here. A can react to this C. If too much, A can, or possible that A can react with C. And once it reacts, it will be almost impossible to find out what was the concentration of B or identity of B. If it does not react in that way, even then, we will be not very precise or very correct to find out the B. So the point is, we should be very careful in adding A to B so that C form, and when all of B at the moment, at the micro moment that all B finished, we stop the reaction, and then that is the most precise. But always, you know, we are human, we are not robots, so we cannot rule out any error. We are prone to error, right? So there is some error. So we are going there slowly. What type of error and what error, and why? How should we reduce those error? So concentration of the solution, and as we said that we will find the concentration of B unknown, which is by as referred to the molarity. Molarity is mole per liter. So how many mole of that solution in 1 liter of solution is there, or how many mole of that species or of that component in 1 liter of solution is the molarity. All right, how many moles of that solution, of that compound? I want to say something, forgot. Okay, how many moles in that solution in liter? Oh, okay. So it is not in chemical in the lab. We do not always put in this big volume in liter, because afterwards it is a waste, right? So what you can do, what we do is, or you always make it a small amount, small volume. Sorry, not amount, small volume, like 50 milliliter, 20 milliliter, 100 milliliter, like that. So if I want to make it 50, 100, 20 milliliter, what we do is I will convert that 50 milliliter to liter to know the molarity. So never use the milliliter or any other thing than liter to calculate the volume, strength, and molarity is the strength of the solution. Now we know this equation where we are very familiar with this. C equals N over V, or N equals C into V, right? N equals C into V, or C, both are the same thing actually. So now it says that calculate the amount in mole of solute present in 20 milliliter of 0.255 molar sodium hydroxide solution. So 20 milliliter, and this 0.55 molar, 0.255 molar sodium hydroxide means 0.255 mole in 1 liter, right? It is 0.255 mole in 1 liter of sodium hydroxide solution. So what is the number of moles will be? Well, N equals C into V, that we know, so that we can just put the values here, plug in the values here, and then we will get the correct whatever we want to do or we are looking for. So 20 milliliter, of course, we have to convert it to liter. So 20 milliliter converted to liter, and then it will be liter, and this is the number of moles per liter, right? So N equals C into V, and then we find this is the number of moles, and it is a 3 significant figure. This is a 3 significant figure. When you count the significant figure, 10 powered is not counted. It is not counted here. Only the rest of this is significant figure. When we count the significant figure, we count only the rest of it. So if it were 0.050, let's say, I'm just giving an example, 10 power negative third, right? So it will be 3 significant figure as well, right? It will be 3 significant figure as well, because it is 3. I should put it in this way actually, because this is 3 significant figure, and when you count the significant figure before the decimal, we do not count that one. So 3 significant figure, and if it were 5.100, it would be 4 significant figure that way. If it were 0.5100, it would be still 4 significant figure in that way. So before the main figure, the decimal places, the 0 is not counted. That I think you all know that one. Question B says that calculate the molarity of a solution when 2.1 gram of sodium bicarbonate or sodium hydrogen carbonate dissolved in 1 liter of solution. 2.1 gram of sodium bicarbonate or hydrogen carbonate dissolved in 1 liter of solution. In molarity, it is asking us to find out the molarity, moles per liter. It will be, yeah. Yes. My card? Yeah, having it. Yeah, no problem. Okay. So we want to find out the molarity. That means how many moles in 1 liter. The good thing is it is already in 1 liter. So we do not have to convert that thing. So what we have to convert it, we have to find the number of moles now. 2.1 gram means how many moles, right? And number of moles is mass over the molar mass. So mass is 2.1 gram and the molar mass of sodium bicarbonate is 84 gram per mole, right? So we know that in 2.1 gram, there will be 0.025 moles of sodium hydrogen carbonate or sodium bicarbonate, both are the same thing. And this is in 1 liter. It always says that it is in 1 liter. So since it is 1 liter, it is mole per liter, it's the molarity. Another one, the question says that calculate the mass in gram of solute present in 2.5 liter and 1 molar of sucrose. This is the sucrose that we eat as a sugar, right? So how many gram of sugar will it be if we had 2.5 liters of it and the concentration of the solution, let's say we prepare it 2.5 liter in a jug or in a beaker. It is 2.5 liter, and we know the concentration of sugar, sucrose here, it is 1.5 molar. 1.5 molar. Right. So this is how many actually. If you ask your, let's say you ask your grandma, your mom, that mom, how many gram of sugar you put in the drink, and she gives you the value like 2 gram, 5 gram, then you say, okay, it's this much molar. So if your mom or grandma has chemistry education, I mean, she knows chemistry, then she will understand what you mean. But if she doesn't, then she will be shocked at what you're talking about, right? So this is, I'm telling that it is for a general person that we understand gram. Not for only those who are studied chemistry. If even I tell you that, okay, I give you 5 moles of 5 moles of what do you call it? What else? Sugar, already talked. 5 moles of starch. I'm giving you 5 moles of starch. You will, or me, I will also have very hard time to imagine 5 moles means how big. But if you give me, if you tell me, okay, sir, I'm giving you 10 grams of starch, I will have the idea in my head that, okay, 10 gram means this much. 5 moles means how much we don't understand. So that is why we will have to always back and forth. We go from gram and then molarity, back and forth. Molarity, we need to understand the strength, but gram, we need to understand ourselves that how much, roughly how much we need it. But if again, in other way, reverse way, that you are going to the lab and I tell you that, okay, add 2 gram of sodium and 5 gram of HCl and tell me how's the solution. We will have a difficult time to understand. But if I tell you 1 molar of sodium hydroxide, 1 molar of HCl, we understand roughly that what we are expecting from that solution. Enough talking, yeah? Okay, so 2.5 liter of 1.05 molar of sucrose we are adding in the solution, or is added. So from there again, N equals C into V. From there we find the number of moles of how much of sucrose in the solution or inside. So we understand it is 2.62 moles. 2.62 moles of sucrose we have in this solution. And then this sucrose, what is the, we understand that this is the number of moles. How many grams of sucrose will be there? So we just multiply with the molar mass of it. So it is 896 gram of sucrose. That means almost a kilo, right? Almost a kilo of 1 kilo of sugar you have to add in 2.5 liter to get 1.05 molar of sucrose. Can anyone tell me that how many molecules of sucrose will be there? How many molecules of sucrose will be there? Can anybody tell me? Molecules. How many molecules of sucrose are in there? Like this is 1 molecule. Can I take another color? Yes. Okay. So this is 1 molecule. This is another molecule, another molecule, another molecule, another molecule, another molecule, another molecule, and thousands. I am assuming it's thousands. Can anybody tell me how many? Can we know? 1.57 times Brian. Okay. 1.57724 times 10 power 24th. Okay, good. Did you get it by multiplying the Avogadro's number with the number of moles? I didn't do it, but yeah, if you have done it, then yes. So number of moles in 1 mole, there is 6.023, right? Times 10 power 23rd number of molecules in 1 mole, right? So if I have 2.62 moles, so we can just multiply 2.62 and then we will know how many molecules of this sucrose is there, right? So thank you for those who replied. So this is the molarity, and then the done. Thank you. Okay, so other units of concentration that we sometimes you will be using as well in our chemical calculation is the gram per liter, right? This is interesting and this is sometimes useful for us. Gram per liter. When we are not really looking for the number of moles or doing the reaction, we just want to know that roughly how much the the material inside the solution, we can just express it in gram per solution. But we do not usually show it much, only for reference. So this is a much layman style. You can express this way to other your friends. They do not understand, or they do not study chemistry. You can tell them, okay, in this solution there is 890 gram of in 2 liters. Sugar in 2 liters. So in that way, they will understand. And another one is weight by weight volume. All right, volume, weight by weight percentage. Weight by weight percentage. That means gram of solute in weight, and the solution is also in weight. All right, so gram of solute is almost all the time it is in gram. It will be given most of the time that, okay, I give you 10 gram of sugar, 10 gram of salt, 10 gram of potassium hydroxide, 10 gram of sodium hydroxide. Almost all the time it is in gram, but it will be said that dissolve in 1000 liter, dissolve in 100 gram, 100 milliliter. So in that way, the liquid phase will be given you in a liter, volume, milliliter, cubic centimeter, deciliter. So this type of thing in volume unit. So we have to convert that volume into gram. And how do we convert that into gram? We have to take into consideration the density of those solution. D equals M over V, right? So if we want to know the mass of the solution, then we will just multiply density with volume. All right, so that we will get the mass, and by this way we will convert it to gram, and then weight by weight percentage we will get in that way. Volume percentage. How do you get the volume by volume? Now it is in the other way around, that gram of solute, we convert it to volume. And most of the time, this volume percentage, it will be referred to for those material that is in originally in liquid form, acetic acid, HCl. These are already in volume, so volume by volume percentage we also can express. That means volume of the solute. Okay, before that, do we know what is solute? Solution and solvent. There are three things, right? Solute, solvent, and the solution. So, and the solution, S-O-L-N, I'm not writing, yeah, solution. So let's say this is a beaker or a jar. There are some water inside the beaker or inside the jar, and now, or water or any other liquid, let's say it's the liquid inside. So this is the solvent. It is the solvent when there is nothing else. Sorry, it is not S-L-O-N, vent, S-O-L-V-E-N, it is the solvent, right? I am adding some solid or maybe liquid. It doesn't matter if it's solid or liquid. I'm adding something which is a small amount, very small amount of something that is I am adding is the solute. It is the solute I'm adding. I'm adding the solute will always be added to the solvent. And the whole thing after being added, the whole thing becomes a solvent. It becomes a solvent after the whole thing, right? So solute is always a small amount. Solvent is always big amount. All right. So this is the volume by volume. ppm, parts per million. All right, parts per million. When the solute is dissolved in 1 million of parts of that solute we are dissolving. So this is the parts per million, ppm. So gram of solute per million gram, all right, or milligram of solute in 1 liter of solution. In both way, we can understand that this will be the parts per million. So one part of let's say 1 part of sodium, 1 part of sodium in 1 million part 10 power 6, yeah, 10 power 6 parts of sand. In the sea, let's say in the sea, when we go the sea beach, we walking on the sand, we see if 1 part of sodium we find in 1 million part of sand, we will call this 1 ppm of sodium is in the sand, or the concentration is 1 ppm for that. So same goes for the billion, but we will not be using for our case. This one is very small, so it will be 1 billion, so 10 power 9 it will be. And most of the ppm and ppb, these things are used for environmental or very trace amount when we study the air or air pollution, this type of thing mostly, or physical health issues. Question 1D says that convert 0.55 mole of per liter of HCl into weight by volume percentage. Now, per liter, it's already in volume, right? It's already in volume. What you have to do is we have to convert this 0.55 mole of HCl in, since it is in liter, that's what I'm saying, that it is already in volume. But this number of moles of HCl, we have to convert it to gram. So 0.55 liter mole per liter of HCl means how many gram? We find out that it is 20.1 gram of HCl. And now it is in 1000 liter or 1000 milliliter, sorry, 1000 milliliter. So that we just divide by 1000 and then multiply it with 100 percentage. We take the percentage, so it will be 2.01 percentage. Okay, so standard solution, a standard solution with accurately known concentration called standard solution, and substances. I was discussing about the standard solution. What we use to produce a standard solution? What do we produce? What do we use to produce a standard? We always use the primary standards to produce a standard solution. What is a primary standard? Right. And if there is a primary, is there anything called secondary? Is there anything called tertiary? Secondary. Is there anything called tertiary? Or there is only something tertiary, or only there is something we call just primary and that's it. So there, the primary is the solution that it is readily available and it does not, it is not very sophisticated. All right, that means it does not decay or it does not become it does not become impure very easily. It's very stable, it's very robust. It minimizes the effect of error in weighing, stored without much care taken. You can just keep it nicely. I mean, simply you can keep it. It will not deteriorate over time. So those are the properties of primary standard, and should be inexpensive. Okay, it cannot be very expensive. So primary standards are sodium carbonate, sodium borate. Of course, in that there will be 10 molecules of water in that, in bases. Among acids, there are hydrated oxalic acid, potassium hydrogen phthalate. Those are the among the acid, the primary standard. Yes, there are secondary standard. All other things that are not primary, we call secondary. There is not tertiary standard. All right. So only primary and secondary. Those primary are very stable in normal room temperature. They are stable. They does not need any special arrangement to keep them to be intact. You can just keep it nicely, a simple jar, and then just keep it airtight as much as possible, and they will be okay. Secondary standards are not like that. Secondary standard is very much reactive to the atmosphere, and it will not be in pure form, and it is hard to measure or weigh it. So to take or do the calculation. So these all things are secondary standard. Now the question says that a student wishes to prepare 500 milliliter of standard solution of any base of concentration of 0.25 molar. Molarity is 0.25. All right. Would it be better to prepare the solution using solid sodium hydroxide or anhydrous sodium carbonate? Sodium hydroxide, as I just mentioned in the previous slide, that it is hygroscopic. It is hygroscopic, right? It is secondary. It is hygroscopic. That means it absorbs moisture from the air and react with carbon dioxide also. So you cannot rely, you just leave it for half an hour and you come back after half an hour. It is not the same thing. I mean, it is not the same pure thing. So we cannot use it. We have to take the primary standard, that is sodium bicarbonate. And it says that concentration of 0.25 molar with 500 milliliter. So how much of sodium bicarbonate should we be taking? Right. Sodium bicarbonate, it says that concentration is 0.25, 0.25, yeah, 0.25 molar and 500 milliliter. So 0.5 liter as well. From 500 milliliter, we are converting to liter, so it becomes 0.5 liter. So it will be 0.125 moles. The amount of sodium carbonate, right? Sodium carbonate, that amount is 0.125 mole. Now, if I ask you that, do you know what is 0.125 mole? Can you give me 0.125 mole? We will not know 0.125 moles, how much. But if we know the mass or weight of that solution, 0.125 mole, then we will be able to find out the amount that will be required. And that is 0.125 moles times 100%, sorry, the molecular mass of sodium carbonate, right? So that is 106 gram per mole, and then we find it is 13.25 gram of sodium carbonate is needed. How do you prepare it? There is not only the calculation that we have to know, we have to know how do we prepare it exactly. And unfortunate that we would be in the lab, you have to do it, but since no lab now, you will not be able to. Oh, by the way, is this Thursday is holiday here in Malaysia. All right. So those in Malaysia, you know that is the holiday, 16th of this month is Malaysia Day, and for that time we will not have any lab. So I have to, there is no other choice because there is no other reserved date for us. So I will do the pre-recorded session. I will post it on Canvas, the pre-recorded session, and the data will be given to you guys so that you will come up with the lab report next week. Okay, so yeah, this is it. And solution 2 that says that, all right, so steps in preparing a standard solution. How do we prepare a standard solution of sodium carbonate? We will take exactly 13.25 gram . 13.25 gram of the sodium carbonate, and I will put it in the volumetric flask. This is a volumetric flask that it is tall. The neck of the bottle is, it is slender, upright, but the bottom is round shape. It is bulb shape, round shape. Of course, at the base, there is a flat so that you can keep it on the table. And here, so I will put all these from the weighing balance to this through the funnel. This is the funnel, right? This is the funnel. I will use the funnel so that it does not spill, it does not fall outside. And slowly I will channel it through this funnel at the bottom of this volumetric flask. And then I'll start adding water. I'll start adding water. I'll put water not drop wise, but half fill, only half fill, not full. Don't just top up to everything till this is the mark. Actually here it will be 100 milliliter. It is in 100, 500. This is 500 milliliter. So there are different shape or different volume of the bottle, volumetric flask. You can find 500 milliliter, you can find 1 liter, you can 5 liter, you can find 150, 10 milliliter as well. You can find it. So according to this volume, this is 500 milliliter, and till this mark, it will be 500 milliliter. It will be 500 milliliter until this mark. When the water rises up to this mark, it will be 500 milliliter. Not here. We do not know if it goes beyond that line, above this line, we do not know how much. So it will be considered it is wrong. It's already a mistake. It will be considered. So here I will add the water, half of the water I will add, and then I will shake it nicely. I will give a good shake, right? I'll dissolve all the sodium carbonate. I'll make sure that all the sodium carbonate is dissolved, and then I will add another half, 2/3 of the bottle of the volumetric flask water, and then I will make it invert, and of course stopper first, and then I make it nicely move and then shake it nicely, gently, so that I make sure all these sodium hydroxide mixed well. And then I will top up until here, slowly, very carefully, so that it does not cross this line. And once it is touched here, we understand that this is 500 milliliter of sodium hydroxide, solution of this. Before I move to the acid-base reaction, I would like to take 5 minutes of break. Okay, so please have 5 minutes of break, and I'll come back after 5 minutes. But if you have any question, please let me know so that I can talk. Okay, I think it's 5 minutes already. All right. Now we are going to the acid-base reactions. So as at the beginning we are talking that acid and base, when they react, they will produce water and a salt. But before we move to the more detailed or, you know, what do you call it? Understanding of acid-base reaction, we need to understand what is acid and what is a base. What is an acid? Can anybody tell me what is an acid? Can anybody tell me what is an acid? Hey, where is my background? Nur Farah, proton donor. Yes, thank you. Anybody want to chip in? Brian is typing and is taking time. A chemical substance that have hydrogen ions. All right. Anyone else want to say anything? Eric. Better is better to talk, isn't it? Okay. A solution that has a pH level less than 7. Okay. This is interesting, actually. It's getting interesting. Brian is typing something. Okay, so let's start from the last one, Eric. A solution that has a pH level less than 7. Yes, but it is not an acid. The solution called acidic solution, but not necessarily the solution is an acid. Probably there is some acid inside that solution. That's why pH goes down below 7, right? So it is not an acid, and it is not acceptable, and it will not be taken. So it is good that you bring it out, otherwise it will be a mistake for you, right? If you write this in the exam, it will not be correct. Brian say a chemical substance that have hydrogen ions. Yeah, it's only partial truth. It is not always the same thing. What is my background? Okay, hold on. So it is. So it is not the 100%. There are many other things that even though it has hydrogen, it does not work with as an acid. Have you seen NH3? NH3, that is called ammonia. There are 3 hydrogen in it, but it is not an acid, it is a base, right? So it is not always the truth that if there is hydrogen, it will be a acid, no. But Nurfara is much more accurate, and it is actually accurate actually, that it is a proton donor. It donates or gives proton. So what does a proton mean? What does a proton mean? Right? Proton, we know that it is in the atom. In an atom, there is a nucleus, and there is outer of the nucleus. In the nucleus, there is neutron and proton, and outer side there is electron, right? We have seen it in atomic structure. But for hydrogen, there is no neutron here, only proton. Interesting. So, and one electron. So, since hydrogen, if there is no neutron, so what is there? Only proton and electron, right? Only proton and electron. When electron goes away, what will happen? Only proton is there. So hydrogen atom will only have proton when there is no electron in it. So that is why it's called proton. And hydrogen ion, that means when this is a hydrogen ion, when electron goes away from it, it becomes positively charged, right? We have seen it from the isotope and then this calculation. So when the electron goes away, it becomes positive. So that means no hydrogen. One electron go away means there is no electron in the hydrogen atom. So there is only one proton there, nothing else. And that is why it's called proton. The hydrogen is actually a proton donor, not a acid is a proton donor, not a hydrogen donor. All right. So it can donate a proton. But Arrhenius, though, he said that acid is a hydrogen. Who gives hydrogen is an acid, and who gives hydroxyl is the base. But that is also a little bit problematic. It gives us a good idea, but it is not 100% correct. So we say that, okay, whichever gives a proton, that is loses a hydrogen ion, right? So it is an acid. And when ACl, that is a hydrochloric acid, is in the water, right, is reacting, let's say it's reacting in the water, what is happening is it is an acid. That is why it is donating the proton. It's donating the proton to water. So the hydrogen is going here, right? And that is why it becomes H3. It was 2, it becomes H3, and since it's H3, it becomes a positively charged because one positive charge comes here. It was neutral before. All right, so this is one thing. Another thing is HCl, after losing hydrogen or hydrogen ion or proton, what is left? Chloride ion is left. It's not chlorine, yeah? It is chloride ion. It's not a chlorine anymore. Chlorine is Cl2. It is not a chlorine, it's chloride ion. So only the chloride ion is left, right? So it loses hydrogen ion and water gains the hydrogen ion. So the leftover from the acid is the conjugate base, right? Before that, sorry, conjugate gas, okay, you know, good. But this is an acid. This is an acid, HCl is an acid. Water is the base here, isn't it? Because water is accepting this proton. So it is a base here. It is working or acting as a base. Base is what can accept proton. So water is a base here. An acid is donating the hydrogen to a base, that is H2O. There's the water. Now, hydronium ion is formed, or H3O plus is formed, and chloride ion is also formed. This chloride ion is the conjugate base. This is only the leftover thing from the acid, right? This is only the leftover thing of the acid of HCl. So this is a conjugate base of the same acid. So this is the conjugate base of the same acid, HCl. Chloride is the conjugate base of same acid. for base as well, when ammonia is a base, because it does not donate hydrogen, rather it accepts a proton, right? It accepts a proton, so it is a base. And in this case, you see, water is so mysterious. To some, it acting as a base, so to some, it's acting as an acid. Yeah. So in this case, it is acting as an acid because it is donating one hydrogen. How? This hydrogen goes from ammonia to goes from water to ammonia, and then previously ammonia was 3 hydrogen and it was neutral, but here it becomes positively charged and 4 hydrogen with it. Right? There are 4 hydrogen now. You see, it was 3 on left. So that means on the reactant side, it was 3. Now in the product side, it becomes 4 hydrogen. And since this hydrogen is coming from H2O as a proton, this is proton, so it is carrying one positive charge. It's adding this positive charge to this neutral charge ammonia and increasing the positivity charge. So NH4 it becomes. All right. So what is the leftover from the acid? The leftover from the acid is OH negative. Hydrogen goes away from here, so OH negative is only staying. So this is a conjugate base for the acid. All right, where is the conjugate base for the acid? Conjugate base for the acid. Now for the base as well, since it was neutral and then there is one more hydrogen is added to it, the hydrogen is added to, and it is not neutral anymore. That means it has a positive charge. That means it is not stable anymore, because it's when it is neutral, that is always stable, much more stable than the positive or negatively charged. So it is positively charged and it has excess hydrogen. So what it is able to donate the hydrogen to something else, probably not here, but maybe something else comes along, and then it is able to donate this hydrogen, excess hydrogen, and go back to this ammonia again. So this is acid. This acts as an acid, and that is why it is a conjugate acid from that base. So if in the problem, in the question, I mean, in the exam, it says that, okay, show the conjugate acid and base, you have to show in this, and you have to explain in this way as well. Why do we call it conjugate base? What is changing? What happens? What are the changes occurs that it becomes a conjugate acid or base, right? So don't make mistake. Students usually just show, oh, this is a conjugate base. But why? What is happening? What the changes occurs? We have to understand that one. The strength of acid and base. We know that there are strong acid and weak acid, right? Strong acids are those which dissociate fully in the water. We add in the water few drops of the acid and it ionizes. Ionizes means HCl. It is not negative, and this is just an arrow to show that this is one, this is another one. So this HCl, when I add water, it will become like this, 100%, all of it. There will be no HCl together in the water. It will be H3O plus and Cl negatively charged. And sodium oxide as well. So it is very strong base. So when we add in the water, it will be sodium hydroxide and then sodium hydroxide as well. It is very much, sodium hydroxide will be strong base, so it will be ionized as well. For weak acid and weak base, this is vinegar, or we call it acetic acid, is a weak acid in the water. So when it dissolved in the water, what will happen is it will ionize in this form. It will ionize in this form, but it's a very small amount, mostly 97% of this acetic acid will be as it is in the solution. All right, it will be as it is in the solution, 97% of it. It will be in the CH3COOH altogether. The carbon is holding 3 hydrogen here, another 2 oxygen there, and 1 hydrogen on my head, something like that. I'm just making it to make some fun, but yeah, all of them staying like a family. Only a small bit of it will be going to dissociate. So that is a weak acid. And same goes for the weak base as well. They do not dissociate appreciably. It's a small amount of them will be as dissociated. So this is actually equal sign. Okay, so in each of the following equation, identify the acid and bases, name the conjugate acid and base as well. So this is bisulfate ion, and when we are adding water to bisulfate ion, hydronium ion is formed and sulfate ion is formed. That means this HSO4, 1 negative or just negative ion, this is able to donate the hydrogen to here, to water, right? It is donating the hydrogen to this water, and it is producing hydronium ion. So this is an acid in this case. It is an acid. And this is the conjugate base of that acid, conjugate base of this acid. And water is a base here, and hydronium ion H3O plus is a conjugate acid of this base. So every acid will have its conjugate base, and every base will have its conjugate acid. And same thing goes for here as well. You can later see. Now is the important thing, that is our titration and stoichiometric problem. What is titration? Titration is neutralizing one species of acid or base by adding a counterpart of it. If it is an acid, we add base. If it is a base, we add acid, right? And then we know the concentration of that acid or base. So by adding a known concentration of acid or base to an base or acid, then we know the concentration of the unknown. So let's say that is the acid 0.1 molar HCl. We are doing as titration reaction. So students perform the sodium hydroxide solution. Sodium hydroxide solution. By titrating it with standard hydrochloric acid. So sodium hydroxide we took, and standard hydrochloric, when it says standard hydrochloric acid, right? So it means that we already know the concentration of that hydrochloric acid, right? We already know the concentration, because that's why it's called standard. So this HCl we took in the burette, and then the sodium hydroxide, 20 milliliter of it. We do not know the concentration, but of course we have the 100 milliliter of it, let's say, or 500 milliliter of sodium hydroxide of unknown concentration. So what we'll do is we'll take 100 milliliter or 20 milliliter from that 100 milliliter and put it in a conical flask, and the HCl we take it in the burette. And then we start doing that reaction. But when the reaction occurs, we do not know the reaction, because our eyes cannot see the molecular level. So what we do, we add some indicators, so that humans are very smart, right? So we add some indicators. So when there is a reaction changes or the product is formed, the reaction, the color will change. right? The color will change. So that is why we add some indicator, and in this case we will be adding phenolphthalein and then do the reaction. At the end point, when the I mean, I think you have the experience of doing titration reaction. When we add the sodium hydroxide, HCl, in the sodium hydroxide, we see that is occurring pink, right? As the drop falls in the solution, at that part it becomes pink, and then suddenly, I mean, or very quickly, it does disappear. And then another drop, and then we see a pink color at the point where the drop falling, and then the color disappear immediately. But after some time, the pink becomes stable, and it becomes stable, and then we shake, the pink goes, the color goes. But at some point, the whole solution turns pink at a sudden time. I mean, suddenly. And then that color does not disappear first. That color does not disappear that moment, or it stays there for some time, 1-2 minutes. After that, of course, it will disappear, but it stays there for some time. So what is happening is when the sodium, I mean, HCl is from here, is falling here at that moment. Here the phenolphthalein that is there, it will become pink. But when it mixes with the other sodium hydroxide in the solution, it mixes with other volume of the solution, it will become diluted, and then it will go away. It becomes the acid becomes taken, right? The acid is not there, acid anymore, and that is why the pink color goes. But when there is not no other base is there, no other sodium hydroxide is there, so when the acid falls down, it is not able to be taken or reacted with the sodium hydroxide, so the whole thing becomes pink. So this is so when it turns pink, we know that the reaction is done, reaction finished. So at that moment, we understand we can take the volume of the HCl that we added. Let's say we started from here and the end point is here. Started from here and the end point is here. So we know the difference. So this is the final one, F, and this is the initial one, I. So if we deduct the final one, my initial one, so we will find the total volume required for it. Total volume required for the solution. All right, total volume required for the solution that we will be finding. So this is it. This is how we will find the volume that required of the known concentration of sodium HCl. And since the volume we know, let's say the X milliliter of volume we know, and we also know the concentration 0.1 molar, right? So we can just multiply with the volume and then find the concentration of this solution as well. But before that, we have to know the reaction, how the reaction goes on. Is HCl plus sodium hydroxide is reacting, and it is 1:1 reaction, so the number of moles will be same. We're going there actually. So identify the equivalence point. Phenolphthalein, if we add, it works in this range 8.2 to 10. Beyond or below this range, it will not be useful. It will not turn to pink color. Methyl orange, it will be pink, and then when in the base form, it will produce yellow, but it will be in this range. It is useful in this range. Bromothal blue as well, it will become blue, and it works 7.6 range. Okay. Before beginning, question number 4, rinsing of glassware. In the lab, actually, we should be doing this. So before being a student, rinse the glassware that is to be used in the analysis. State the correct rinsing process method for each apparatus. For pipette, we will be using deionized water. For conical flask, we will be using the deionized water, because in the conical flask, we will hold the samples. We'll keep the samples or do the reaction there. So, and pipette, we will, for this, just now, the example we saw for the pipette, because in this pipette, this is a pipette, right? We are taking the sodium hydroxide, we are measuring the sodium hydroxide, and in the burette, there is the HCl, right? This is the HCl in the burette. HCl, and this is sodium hydroxide, right? So in the pipette, there is sodium hydroxide we are taking. So we will rinse it. Rinse means just, wash it very quickly, and it is not washing, it's rinsing. So quick wash. We'll use the sodium hydroxide to rinse pipette, but we will not use the burette. Of course, we will not. If we use burette, then there will be a mistake in the calculation or in the observation. And then we will, for the hydrochloric acid, we will only use it for rinsing the burette. Question number B says that this is the reading, all right? This is the reading for our 3 sets or 5 sets of experiment, the same experiment that we have done. Actually, this is your first experiment as well. So pay attention so that it will be easier for you to prepare the report, right? Let's say that we have 5 sets of experiment. We have done 5 times. That is why 1, 2, 3, 4, 5. We have done 5 times. At the beginning, first we have taken 20.20. All right. Volume in the burette, and initially it was 0, and we have added 20.20 milliliter of HCl in the conical flask. For another one, second run, we have taken 40 milliliter or 40.8 milliliter, and then we have added 21 milliliter. The final one, we saw that it was 21, and it was initially it was taken 40. Sorry, final was 40, initial was 21, because the burette, if you have remembered using burette, we start 0, right? Here it is 0, and 50 is here. So the more you add, the more it is the volume increasing. At initially it is 0. And the more you are adding, it is going down, so it is increasing. So it increases to 40.808, and we started from 21. So if we deduct these 2, we will get 19.82 volume. And this way we find 5 different readings. So which one is correct actually? Which one is correct? Number 1, we keep it as a rough titration. We did it just to understand how the titration will go, right? We did not do it for serious purpose. We just wanted to know how this thing will go, what to expect, the titer. So from 2nd, 3rd, 4th, 5th, we become very cautious, very precise, and then we did it. So this 4, out of this 4, we see that 2, 4, and 5, these 3 are very close to each other. Number 3 is a bit deviated, so we do not want to consider this 3. So we will take this 3 and take the average of these 3. All right, we take the average of these 3. So the average of these 3 is 19.82, and this is the titer that we have added. On average, 19.82 milliliter was required to neutralize the base that in the conical flask. Now we know the in acid, all right, the acid volume 19.882 milliliter, and the concentration we already know is 10 milliliter, and 20 milliliter in the pipette and the conical flask we started, right? We remember this is the 20 milliliter we took from the pipette in the conical flask. Is 20 milliliter. Is 20 milliliter as, although we have added 1 or 2 drops of indicator, but that is not counted because that will not take in the participation in the reaction. So this is 20 milliliter of base or sodium hydroxide was taken. So now we know many things, right? So we know the V1, we know the C, we know the C2, that is the HCl concentration and the volume of HCl. Now we have to know the stoichiometry. At the beginning we started the stoichiometry, right? Stoichiometry we have to understand, otherwise we will not be able to proceed. That sodium hydroxide and HCl 1:1 reaction. Once again, 1:1 reaction. 1 mole of sodium hydroxide, 1 mole of HCl. They are reacting together, and they are of course producing 1:1. But since it is 1:1 reaction, the number of moles is 1. Sodium hydroxide number of moles is also 1. So if I have X moles of HCl, I will also have X moles of sodium hydroxide here. All right, I have X moles sodium hydroxide, HCl, I will have X mole. So how many moles of HCl I have? We have to calculate from here. How many moles of sodium? And it is easy, N equals C into V. We just multiply C into V here, and we find 1.982 times 10 power negative third moles of HCl is there. Exact same amount of number of moles of sodium hydroxide should be there, right? Should be there. So now is easy that we find the number of moles of sodium hydroxide in HCl. But how do we know the concentration? We know the number of moles, that is good, but the concentration, how do you know the concentration? Since we know the number of moles of sodium hydroxide, right? So it is in 20 milliliter. Again, the C is N over V. So it is in 20 milliliter. So 20 milliliter, of course, we have to convert it to liter. This 20 milliliter, we have to convert it to liter, and then we divide the number of moles that we got by that figure, and that is why it is saying that C is 0.099, or you can say it 0.1 molar, 10 molar. M. All right, you can round up to 0.1. So this is this is how you define the concentration of it. Another question says that the ethanoic acid content of white vinegar was determined by titrating 20 milliliter aliquot of this vinegar with 0.995 molar sodium hydroxide solution. The phenolphthalein indicator changes permanently from colorless to pink. All right, colorless to pink, and for that it took 20 milliliter, 20.35 milliliter sodium hydroxide. So calculate the concentration of ethanoic acid in the vinegar. All right, so ethanoic acid and sodium hydroxide, they react 1:1 as well. So if we know the number of moles of sodium hydroxide, we will know the number of moles of ethanoic acid as well. Right, but if the reaction is 2:1, 2:1, so that means if I have 1 mole of sodium hydroxide, I will have 2 moles of sodium acetic acid. I mean, not acetic acid, but it was if it was 2:1 reaction, or it is 3:2 reaction, or whatever. But you understand that if 1:1, that means exact same number of moles will be there. So if it is 1:2, double the number of moles will be there. If 3:5, 3/5 times the number of moles will be there. So this is the understanding. We understand that one. And the same way, it goes the same way, and it is the 1:1 reaction. We find the number of moles of sodium hydroxide is 0.02 by N equals C into V from the reaction, N equals C into V. Okay, C is N over V. There is something. So from there we find number of moles. So acetic acid number of moles will be the same thing, and then we divide by the volume of the acetic 20 milliliter that we took into the reaction, or in the practical, or in the experiment. So 20 milliliter we took, and then it is in there. Okay. Question number, another one, it says the commercial concrete cleaner contains concentrated hydrochloric acid. A 25 milliliter volume of cleaner was diluted in a volumetric flask. 20 milliliter aliquot of 0.448 molar sodium carbonate was placed in a conical flask, and methyl orange indicator was added, and the solution was titrated with the dilute cleaner. The methyl orange indicated the change permanently from yellow to pink when 19.85 milliliter of the cleaner was added. Calculate the concentration of hydrochloric acid. So all the information are given. We have to see the hydrochloric acid concentration, and of course we have to know the stoichiometry for the reaction. So now it is 2:1 reaction. So if I have 1 mole of sodium hydroxide, sodium carbonate, N2O CO3, I will have 2 moles of HCl. Right? This is equal sign, and this reaction is nicely balanced out. The stoichiometric ratio is okay. It's balanced. The reaction is balanced. So it is 2:1 reaction. Now HCl, the concentration and volume we find, the base, the concentration and volume we find as well. So the number of moles of sodium carbonate that we know from the number of moles, molarity, sorry, concentration of sodium carbonate we know, and the volume it was required was 20 milliliter. From there we know the number of moles, and it is 1:2, so it will be double. The HCl will be the double of sodium carbonate. So it is become 0.1792, and it is in 19.85 milliliter. That means 0.1985 liter, and this is the concentration of it. Okay. Another thing that to remember, that it was 25 milliliter was diluted to 250 milliliter of the hydrochloric acid, or the brick cleaner was diluted to 250. Why do you have to dilute it? Because if it is concentrated, the reaction does not go smooth, or it will take a long time to do the titration, and also it will take a much of effort and a lot of chemicals, and the reaction will not be very precise. We will not get a very good end point, right? So that is why it is better to do the dilution. But how many times has it been diluted? 25 milliliter was diluted 250 milliliter. So it is a 10 times dilution, right? And this calculation is for this diluted. This is for diluted solution. But what will be in the undiluted solution? We know that it is 10 times dilution. So if we multiply it by 10, we will get the actual concentration that was in the solution. So it is 9.028 moles per liter. And now it is saying the manufacturer specification is 33% weight by weight of HCl, weight by weight fraction. Okay, HCl. Is your result accurate? Calculate the percentage of error. So 33% means 33 gram in 100 gram of HCl. Since it is weight by weight, so 33 gram in 100 gram. 33 gram means how many moles? We can easily find out, right? 33 means how many moles of HCl is there, and that is 9.9051. How many did you get? We get it 0.9028 number of moles per liter, right? So 0.9051, and assuming the density, we have to know the density to know the from liter to gram, as we said before. So if 1 gram has 1 milliliter has 1 gram of weight, so we understand that 100 gram will be 100 milliliter, right? So in 100 milliliter, there is 0.9051 mole of HCl. So in 1000 milliliter, it will be 1000 is 10 times 100, so it will be 10 times as well. 10 times as well, and then it becomes 9.51 moles. Which is 9.05. So how much is the error occurs? Or how much is the difference? The theoretical values was 9.051, right? This is according to the manufacturer. So our knowledge or our theory is based on the manufacturer's value. So 0.9051, and we found it 0.9021, right? 0.0928 from here, or 9.051 or 9.02, and then the theoretical value, we take the theoretical value and multiply with 100% is 25, is 0.25% actually. The difference from what the manufacturer is saying and what we are getting is 0.25% difference. So if the accuracy or the percentage difference is less than 0.5%, then it will be accurate. Less than 5% means accurate. Okay, so this is how we say. So why the results become not accurate, or what are the problem or error occur? There are two types of error: systematic error and a random error. Systematic error means cannot be, it is not in our hand. Okay, it happens in one direction all the time. And we cannot measure it, reduce by repeating. No matter how many times you repeat it, it will always be the same error added up, or it will always show the same error. And it will always show in one direction. That means if we are getting less amount, less volume, all the time we'll get the less volume. If we are getting less mass or weight, all the time it will get the less mass. So this is a systematic error, and this thing occurs if we do not calibrate it, or if we do not take it seriously, then this type of error occurs. So what we'll do, we must calibrate it. We will know, standardize our instrument and all the apparatus before we proceed for the experiment. Random error. It happens in all direction, all right, and it is not in our hand mostly. The random error, it happens like the voltage fluctuation, right? If the voltage fluctuation happens, all the temperature up and down happens during the lab. temperature or the pressure up and down happens. So we cannot actually control this thing. So the random error can occur sometimes. But systematic error, we should always avoid by doing the calibration and by doing this, what do you call it? Standardize our instrument and calibrate it. Sources of error: rinsing the glassware. If we do not rinse it properly, the error will occur. Detecting the end point if we have problem or vision, or if we cannot see it clearly, or this is not transparent, the glass, we will not be able to see it or detect it, and there will be an error occur. Contamination or degradation of chemicals, like we did not know, or if we did not take proper precautions in storing the chemicals, then the error occur and it will be almost impossible to find out or pinpoint where the error occurs. Measuring error also can. So avoid common error in the titration. We should, when we fill it up, the burette, we will always check this part. This is the tip part, okay? And then sometimes students never check that there is a bubble. There always can be a bubble. That shows the big bubble is here, and this bubble is dangerous. We have to remove this thing. Constant swirling, the students do not do constant swirling, they do too vigorously that the solution jumps up and goes out or spill. Why we should always wipe the tip, all right, inside the conical flask, because the conical flask is here, right? So after we stop or we do the reaction or do the titration, we should wipe down. And we should always see the meniscus. Some students read this upper part. It is not the proper way. It is if we look at the burette, we will see that this is a concave, I think, and this is convex or straight, twist, more straight line here. So we will always take the bottom one, which is straight, not this part. Some students take this reading, it is wrong. All right, this is correct. So this thing we have to understand. Okay, so this is another problem, which is 1:2 reaction, and we must find out what is 1.2 gram of antacid tablet contains 80% by mass of magnesium hydroxide as the ingredient, active ingredient. What volume of 0.1 molar, 5 molar hydrochloric acid could the antacid tablet neutralize? The antacid tablet is the same thing that we take for acidity, right? Or if we have acidity, so we take it. So this one can neutralize the hydrochloric acid, and then this reaction is going this way. The information is given in that it is 0.15 molar of hydrochloric acid. How much hydrochloric acid should we be adding to neutralize this 1.2 gram of antacid tablet, which contains 80%? It is quite okay. 1.2 gram of antacid tablet, we know that it is okay. And 1.2 gram of antacid tablet means how many moles, we can also find out. But problem is 80% by mass magnesium hydroxide that is contained. So 80% of 1.2 gram is 0.96 gram, right? So 0.96 gram, that is our active ingredient of magnesium hydroxide. How many moles is this? So this is the number of moles of magnesium hydroxide, and HCl will be required exact double number of moles, because this one is to 2 mole. If 1 mole is here, 2 moles will be required. So 0.16 mole will be required, double moles of that. And we understand that this is the number of moles will be required of HCl, and it is in 15 milliliter. Sorry, 15 moles per liter. The concentration is 0.15 moles per liter. So N V equals N over V. If we just divide these two things, this mole and mole will cancel out. Only the liter will remain. So it is 0.02196 liter, that is 222 milliliter of HCl will be required to neutralize the anthracite. So this is our what do you call it, summary, and this is it. Anyone has any questions so far?
Sir, hi sir.
Yeah.
Sir, this question is not about today's lecture, but it's about our lab safety, sir.
Mm.
The lab safety submission today is the last, right? That should be the last day, right?
No, actually, lab safety, you can submit. Is
Yes,
it?
sir, but I cannot find the file, sir, in my canvas. I'm not sure.
Okay, I will make it open, but yeah, you can submit. Whoever wants to submit, please submit. Unless we start the lab, we will not be required it. Okay.
Oh,
But
so is it
I'm going.
compulsory or?
No, it's not compulsory. It's not a compulsory since we do not have a lab, so it's not compulsory.
Oh, okay, sir. All right.
But I will make it open, so for you, whoever wants to submit it can submit. All right.
Sure, sir.
I had some Menti question, but the time is up. All right, so I will see you on Friday then, because Thursday is a holiday here. But please keep an eye on the canvas for the pre-recorded session. All the best. Thank you very much. Take care.